Okay, so I guess we can start. First of all, thanks for coming. I'm Luca Gibelli, founder of Skylable. We're doing a distributed object storage, open source. So today's presentation is about the limits of storing massive amounts of data in a traditional storage or a network, and the limits of using the S3 protocol or an S3 compatible cloud. I will show you why Scalable SX is better, what we do better, what we tried to fix, and hopefully succeeded, and some use cases for our software. So first of all, a bit about our background. The team behind the Scalable is the same team that founded ClameV in 2002, 2003. There are all four founders come from ClameV. You probably know ClameV. It's the most famous and widely used antivirus, open source antivirus. It's deployed on millions of servers, protecting billions of mailboxes. It's used by Google for Gmail, for Google Drive. It's used even by Facebook to scan the pictures that you upload to your Facebook account. To find if you're using steganography to hide some pirated software or nasty stuff into your images to leverage Facebook CDN. We were acquired in 2007 by SourceFire, which later in 2012, 2013 was acquired by Cisco. So now ClameV is maintained and developed by Cisco. They made a commitment to keep it open source and keep the development active, so you don't have to worry if you're running ClameV on your servers. It will not go away anytime soon. So from when SourceFire got acquired, shortly before SourceFire got acquired by Cisco, we decided to move to a new project, to do something new. After developing ClameV for 10 years, we felt that it was time to look around and find other problems to solve. So we founded Scalable with the mission to develop an easy-to-use and secure distributed storage. We bootstrapped for 1 year, and about 1 year and a half later, we got a seed round by Sunstone Capital. You might know Sunstone Capital if you are into graph databases. So graph databases are that thing that tells you like this, so you may like also, or for example, on Netflix. Or when you go on LinkedIn and you are connected to somebody and you see you are connected to this guy, so you might know also this person. So all that stuff comes from graph database, and the most famous one, which is also open source, is Neo4j, which is also was also founded by Sunstone. So how did it happen? Why did we move from cybersecurity, from the antivirus market to the storage market? Well, one of the most pressing issues that we had when we were developing ClameV was storing the malware. So we were getting around 100 gigabytes of, 10 gigabytes of new unique malware per day. So every time we made a database update with the new signatures, we had to analyze all the signatures and, all the old malware samples and the new ones. And we had to do it quickly because we had to react quickly. Sorry, the Wi-Fi is taking over. We had to react quickly to new outbreaks of malware, so we had to have a fast access to a huge collection of malware. And that was hard. So we started with NetApp, storage area network, which soon became too small. So it took almost 12 months to get an upgraded model. So we simply realized that it was not working out. And especially speed was not that great. It was not as fast as we wanted. So we always had the problem that we were adding more shelves, but you can add more shelves up to some point, right? At some point, you just have to buy the newer model. You cannot keep adding floors. So we started looking around for open source solution for distributed storage, and we tried most of them, and we were not really happy with the results. Most of them were complicated to set up and to maintain. Some of them were not, well, most of them were also not fast enough for our needs. So we started analyzing the implementation decisions of each project, since we were open source developers and the software was open source. We had a look at where were the bottlenecks, where were the problems, and we gained some know-how in the field while developing ClamAV, but simply we didn't have time back then to fix them or to help with the development of that project. So when we decided to start a new project, we had some background in the storage arena, and we used it. We decided to start something new because we thought that the software that was already available had made some assumptions that were not really needed for our use case. So we started looking at how some projects were doing things and why they had come up with that design, and we realized that some of those things were not really a requirement for our use case. We asked a few questions around, and we found out that there were other people with the same use case as us that didn't need those assumptions as well. So what were those assumptions? Well, it's all about the CAP theorem. The CAP theorem, as you probably already know, says that you cannot have all of these things. You cannot have consistency and availability and partition tolerance at the same time. You have to choose two of them. And what are the different choices that you can make the most common? Well, block storage chooses CA, consistency and availability. It allows to create, it's mainly suited to make to store structured data. As a consequence of guaranteeing consistency and availability, it has to be complex, and it's also often, well, expensive in terms of time and resources to run. File system storage also guarantees consistency and availability, so a similar story. Object storage instead aims at guaranteeing availability and partition tolerance. So the idea is that you sacrifice consistency and get something that is always available and which can sustain the dead of a node. Where is object storage most useful? Well, when you have to store really huge amount of data and structured data, and when you want to use inexpensive hardware. So typically, you get, with object storage, you get the scalability, durability, low price, and it's best suited for backups, storing log files, long-term archival, documents, very large file, media files. So typically, when you start a new project, the first thing that you think is, I need a large file system. I need a large storage. I need a large file system. But this question is not even given much thought usually, and this, in our opinion, was a big mistake. So you should focus on really your requirements and ask yourself, do I really need all the features that come with the file systems? Or can I survive with an object storage? Because that makes a huge difference in the long term. Again, in terms of costs, running cost, and also in terms of complexity of the setup. And what are instead the arguments against using object storage? Well, it's not that easy to use an object storage for your project because it requires support at the application layer. So you need to re-engineer your application to use a few operations. You don't have the flexibility of a file system. So the typical operation that you can perform on an object storage are put, get, list, delete. You have to give up on append, so you cannot simply modify a file or append the data to a file, not easily. You have to give up on locking, so you cannot rely on the file system to tell you if another application is accessing your files. And you lose file hierarchy, so all the namespace is flat. When you use an object storage, you see directories, but they're not really directories. They're just fake directories made by extending the name, by accepting slashes in the file name, right? So listing a volume of an object storage takes a lot of time, typically, because you are actually listing all the files in that volume, even if you are listing a subdirectory, because, again, there is no concept of directories. Now, what happens when you use an object storage? As we said, there is no concept of appending a file, and there is no concept of there is no concept of appending a file and no locking. So what happens when you use a typical object storage, old style S3-like object storage? Well, you run the risk of losing a specific revision of your file, unless you enable revisions, obviously, because you might write to it from 2 different applications. And you have to always upload the whole file. So if you just change 1 byte in the file, you have to overwrite the whole file. This means you consume more bandwidth, and it takes more time. S3 does, some S3 implementation do deduplication server side. So when you actually store the file server side, when you store multiple revisions, you just take a little space. You don't write a full copy of the new revision of the file, but you still have to transfer it completely, right? So with our protocol SX, we improved this. We improved the situation with the client-side deduplication, which means that if even a portion, any portion of a file, of an object, sorry, is already stored on the cluster, you will never transfer it again. So it's already there. The server, when the client has to upload a file, it first asks the server, do you already have this block? Do you already have this part of the file? If yes, I will not transfer it. I will just send you the hash of that block so that you can put it in the map of my file, but I don't have to upload it again. So this translates into savings in terms of bandwidth, time, and also disk space. And how does it help with the lack of the append operation on object storage? Well, it effectively implements a kind of append, because when you want to just modify a portion of a file, you just re-upload the whole file, but the cluster will tell you that that part of the file that you didn't modify is already there, and you will not transfer it. Again, it helps with locking, because you can keep as many revisions of the file as you want, and they will take very little space on the actual storage, because you will just store the differences between different revisions of the file. Yeah, this is. So how do we position Skylable compared to our competitors? Well, the thing that we didn't like in our competitors, as I anticipated, were that most of them were complex to install and run. They only supported the S3 protocol, and they didn't have file transfers, resumes, incremental resumes. I have to turn off Wi-Fi. And none of them supported the duplication natively. So there were some attempts to integrate the duplication by using the Btrfs, which is really not stable, not production ready. Especially, it was not production ready for sure 2 years ago. Recently, they made some improvements, but still, it's quite risky to use. So we built all this, we made the setup of Scalable as simple as possible. Our aim was to make a 3-step installation process, something that even a junior sysadmin could do in 1 minute, and implement and add the duplication. So these were our main differentiators. So just to give you an idea of how simple it is to deploy Scalable, this is the the only questions that you will be asked when you do a deployment. So you start by setting up the first node. On the first node, so all nodes are created equal, right? But the questions that you need to answer when you create the first node of the clusters are different from the others. But all nodes are created equal, so there is no concept of primary and secondary, obviously. And there is even no concept of proxy nodes and storage nodes, chunk nodes, which you might be familiar if you have tried Ceph, Swift, LizardFS, for example. So, Swift. So all nodes are created equal, which means that it's simpler to manage and to scale out, because you don't have to think about creating a layer of proxies, a layer of storage nodes. You just keep setting up nodes the same way all the time. So the first node, when you set up the first node, you just install our package. We have package repositories for Linux or majors distribution, from CentOS 5 to CentOS 6, 7, Debian, stable testing, Ubuntu from 12.04 to the latest. We support Omnios, if you like, ZFS, so Open Solaris, Illumos, I mean. We support BSD. Yeah, that's it. We also run on multiple architectures, so you can install Scalable on x86 commodity servers. You can install it on a Raspberry Pi, on a Cubby board. We tried to build a cluster with a couple of Cubby boards. We got about 4 megabytes per second from each node, which is not bad if you take into consideration that we were using SD cards as the backend storage. And the Cubby board is really a cheap node. So we support ARM, MIPS, and x86, yes. And also PowerPC. The software is written entirely in C, so it's much faster than other similar software, for example, written in Python. And it made it also very portable. I mean, we ported the same client also to Android in like a couple of hours. Never tried writing anything for Android, but we got a request for that, so we ported the libsx, our client library, to Android in a couple of hours. So that's the advantage when you start, when you take the hard way, when you, instead of going the easy way with Python, which seems easy, but then you face the problems later, especially performance problems. We took the hard way with C, by developing this in C. It took some time, took some more, well, much longer than we expected to develop it, but it's paying off. So back to the installation. I diverged. So to set up a node, you just run a single command, sx setup. You have to choose a DNS name for the cluster. I called it sx.foo.com. You have to choose the directory where you want to put the actual data. You have to choose how much space you want to allocate on this node, and the IP address. And then, of course, you are asked if this is the first node of the cluster. You just push enter, the default value, confirm all the settings, and you have the first node of the cluster up and running, which is already, sorry, let me, okay, which is already usable. You can already start uploading data. Of course, you can only create volumes with replica 1, because you have only one node. So this works differently from other projects which you might be familiar with, like React.cs, which by default starts creates a replica tree volume, even if you have like 2 nodes, for whatever reason. Initially you can create volumes only with replica 1 and start uploading data. And then you can keep growing the cluster. You can add more nodes and create volumes with higher replica counts. So this is the setup of the second and the following nodes. Again, you have to enter the cluster name, sx.foo.com, the directory where you want to store the data, the size of the node, the IP address of this node, the IP address of any other node of the cluster, not necessarily the first, any other existing node, and the admin key, which is the actual authentication that is used to connect, to join the cluster. And that's it. Then if you use self-signed certificates, you will be shown the fingerprint of the SSL certificate for better security. So you can verify that you are connecting to this node to the real cluster. Accept the certificate and you are done. You have joined the node. What happens at this point? If you have already uploaded some data to the cluster, it will start automatically a rebalance process which will redistribute the data proportionally on all nodes, depending on the size of the nodes. So this is very important. We use consistent hashing, like most products. So this means that you can have nodes of different sizes. You can have a node with 10 terabytes and 2 nodes with 5 terabytes, and you will have 10 terabytes replica 2 of usable space. So you don't need to create nodes all equal. They can be different, and they will store a proportional amount of data to the size of the node. The rebalance process, as I said, is totally transparent to you. You don't have to worry about it. When you join the node, it will start automatically, and it will redistribute the data, making sure that all the replica count is satisfied. So what are the main benefits of SX cluster? We took the best of 3 things that we really liked. One is rsync, incremental transfers. One is S3, so we made all of our protocol RESTful, so it's totally proxy-friendly. You don't have to worry about anything. It uses HTTPS by default, so you don't have to worry about encryption. If you have used Swift, if you have set up a distributed Swift cluster, you probably face the problem of authentication, right? In Swift, all chunks, all storage nodes communicate insecurely with the proxy nodes. They communicate in clear text, and last time I checked, they didn't even have authentication in place. So the documentation, at least until the release in January, the one that I checked out, suggested to set up a VPN over which the Swift nodes should communicate. This complicates things a lot because you have to make the VPN redundant, make sure that it's always available if you want the storage to be always available. So we solved this problem by making everything authenticated and encrypted by default. We use proxy-friendly protocol, contrary to Swift, which requires opening 1,000 ports. Many of them are dynamic ports. And we made the most important improvement that we made compared to S3 is that we made the speed grow linearly with the number of nodes. So thanks to consistent hashing, the data is distributed across all nodes. So when you download or upload the data, you are talking to all nodes in parallel, up to a certain limit that you can choose. So if you want to talk to 5 nodes, you can set a limit to 5 nodes, but by default, it will use all nodes. This means that you get better speed, better, and that you can actually grow the speed. There is no single bottleneck. When you use a proxy node, when you use an S3 endpoint, you are limited by the bandwidth. For a single transfer, you are limited by the bandwidth of that node. With SX, you don't have such limit. So we are almost running out of time, so I will go quickly through the use cases. that some of our users found SX cluster useful for some projects that we didn't even, some of them we didn't even foresee, but anyway, let's go through them. So the most obvious use case is S3 compatible storage, so a drop-in replacement for AWS S3. The nice thing is that you get a local S3 cloud, which is obviously faster than uploading to a remote cloud. It's very useful it's used, for example, by 3S data center in Poland, which to allow backing up and restoring servers from a local network at a gigabit speed instead of using Amazon S3. CDN, this is, if you like image sharing services, imgy.org is using Skylable to store and distribute and serve the images. So basically you can create a network of SX nodes distributed even geographically and serve data even over HTTP or HTTPS directly without using the SX protocol, but by using just a plain HTTP, HTTPS. So you can effectively create, if you create, for example, a cluster of 4 nodes and put and distributed them geographically, you have effectively created, and you use a replica 4 volume, you have effectively created a CDN because each location will have a copy of the file and will be serving the files independently. And the nice thing is that you don't have to wait to for the CDN to be synchronized, because when you upload the file to the cluster, it's replicated synchronously to all nodes. Another use case is an hospital, actually a couple of hospitals in Italy, which are using Scalable as a storage backend for, as a storage system for their PACS system, the picture archiving communication system. The PACS system is, in case you are not aware, it's the one that stores your X-rays or MRIs. We are talking about typically 100 gigabytes per exam per patient. So it's a lot of data to store. There is an open source software which basically implements the DCIM protocol, which talks to the X-rays, which is the one used to talk to the X-rays machine, MRI machines. It's called the DCM4CHE. And these hospitals, well, the IT company of this hospital developed the glue, a plugin for DCM4CHE to store the data in Scalable. So they have a multi-tiering policy, which allows to have some exams stored locally, and some exams instead stored in a remote location on a long-term archival, cheaper storage. And so this satisfies also all the ISO certification required to have data always available, even for the disaster recovery. And the nice thing is that we also support, in Scalable, we also support permissions with a quite fine-grained way. So you can choose to write once and read many policies. So basically, what the hospital needed was to forbid to modify an existing exam. So once the MRI or the X-ray exam is stored in the cluster, it cannot be edited in any way. And we fit perfectly in this use case. Another use case, which we really like and which is gaining momentum now, is our white label cloud drive. So on top of Scalable, over the SX cluster, we built a cloud drive application, which is available for Windows, OS X, Linux, Android. iOS is pending approval by App Store. And even a web interface. So probably you are familiar with OnCloud. We built an alternative to OnCloud. Why is it's better than OnCloud? Well, OnCloud still requires you to use a separated system for the storage, which can be an S3 storage or a local file system. But It's basically, on-cloud relies heavily on a database, right? And that database becomes a single point of failure or a bottleneck, if you want to look at it another way. So it's quite difficult to scale horizontally on-cloud. The only thing that you can do is a sharding, which is what they do also, as far as I know, in their enterprise product. But again, sharding, from my point of view, is a bit like cheating, and it brings also many, a lot of complexity and many problems with it. So with Scalable, you don't need to do sharding, obviously. You have no middleware, which does acts as a bottleneck single point of failure. Everything is totally distributed. The Cloud Drive application talks directly to the cluster, where all nodes, as I said, are created equal. We support client-side encryption. I talked to the on-cloud guys. They don't want to implement the client-side encryption because they don't want to implement it in the web interface. So instead, we said, OK, if you enable client-side encryption, you cannot use the web interface. Good grief. And so we implemented client-side encryption, which is a very important feature if you cannot trust the company or the person that administers your servers, because the data is encrypted before it's uploaded to the SX cluster, so nobody can have access to your data except you. And finally, compared to on-cloud, we support incremental transfers. So if you modify a part of a file in on-cloud, then it will re-upload the whole file because it uses the WebDAV protocol. With Scalable, you only upload and transfer the differences. This is very important, especially when you are using the mobile clients. It saves a lot of time, bandwidth, battery, everything. But it's also useful when using large files, multiple gigabytes files on a desktop, because with on-cloud uploading 4 gigabytes, managing a 4 gigabyte file is quite problematic because you have to, every time you modify a tiny part of it, you have to upload all 4 gigabytes. Then we support revisions, but on-cloud does it too, and the duplication comes for free. So I ran out of time, so we just say, yeah, we have also an enterprise edition, which is our business model, right? Which supports LDAP, Active Directory, two-factor authentication. We have a web management console, and obviously we offer commercial support. For our open source edition, we offer support on our mailing list. So I encourage you to try Skylable. It's obviously it's licensed under the GPL, GPL2+. And so try it out and subscribe to our mailing list. And if you encounter any problem, we will help you out. So yeah, I'm 3 minutes late, so I guess there is no time for the question time, or can we ask a few questions? All right. Okay, so any questions? Yeah.
Is the duplication global across a cluster of services, and if so, how does that scale?
Mm-hmm. Okay, so yeah, the duplication is cluster-wise.
Can you please repeat the question for the camera?
Right. Can I? Yeah, with the mic. Okay, so the question is the duplication global across all users? Yes, it's cluster-wide, and it was difficult to implement. So the question is also, how does it scale? It was the hardest part of the project. So when we started the project in 2012, more or less, we thought that it wouldn't be so hard. So we started with exactly by implementing the duplication. And we thought that we would be done in 1 year. It took 2.5 years to get it right. So it was really difficult, but we sorted it out. It scales well from our perspective. We tried so far. The largest cluster that we had was 400 terabytes. So I cannot talk about the petabyte scale yet, but the 400 terabyte cluster was just fine. And the duplication is done with a dynamic block size. So basically, all data is stored with a different block size depending on the total size of the file. So it's totally customizable, so you can just pass a flag to configure and change the defaults. We just set some what we believe are sane defaults, but the truth is that there is no one-size-fits-all rule, right? So you just have to adjust those settings if you want to optimize for performances. So typically, if I remember correctly, we have a 4K kilobyte block size for files under 64K. Then we have a 64K block size for files under 1 meg, and then we have a 1 megabyte block size for files bigger than 100 megs, something like that. So it's totally configurable. The reason we did this is that when you have a small file, you are more likely to get a decent deduplication factor if the block size is small. But for large files, we had really big performance issues when we're using small block size. So we came up with the idea of a dynamic block size to fix that. So when you're using gigabyte files, but we tested even a single, we were able quite easily to store in Scalable a single 20 terabyte file. That was not a problem at all, using the 1 megabyte block size. So, for the camera. Okay. So, any other question? Yeah. Okay, so right now we require using, the question is how do you handle multiple hard drives per node? So right now we require a write, can be a software write, hardware write on each node to store, and we rely on the file system to store our data. So we basically, the block size, the various blocks that we store are aggregated into what we call a container, a data container. And then we have some techniques to recover the unused space, to compact these containers. So basically what you will find out is that you have to mount the write volume, the write partition, put Skylable on it, and put a Scalable storage on it, and you will find if I remember correctly, like 20 files or something like that, huge files that keep growing as your storage usage grows. The ideal setup, obviously, is to use LVM, to rely on LVM, so that you can, if you add more hard drives, you can extend the partition. Yes. Well, it's not a big problem, at least in our production environment. It didn't turn out to be a big problem because we had, the replica takes care of any downtime. So you will never run a replica 1 setup. Nobody does that. The typical use case is with the replica 3. So you can get even if one node goes down because you have to do a file system check or whatever, you can still use the cluster transparently, so it's not a big problem. So far, the use file, we didn't find any problem. Also, it's quite standard. Other projects, most projects that I tried are doing the same, with the exception of Ceph. Yeah. So we did a lot of testing in this sense, and the question is which file system is recommended. And for the storage, we did a lot of testing, and in the end, turned out that X4 was the best option for us. I know that, that there might be different opinions on this, but this is what came up. We do most of our, I mean, I think that it also depends a lot on, to be honest, on the kind of hardware that you use. So we do most of our testing on the Dell 720, something like that. But yeah, I think it really depends on your setup, on the exact machine that you are using. I'm sure that if we repeat the test 10 times, we will get, each one will have different opinions on this.
Is your solution only meant for storing files, like a simple file storage, or could you, for example, also use it to export block devices to integrate it to OpenNebula, OpenStack, or any virtualization system?
Okay, so right now we have basically, so the question, oh no, you had the microphone. The only time that I remembered you had the microphone. Right now we have basically 4 products available. One is SX cluster, which is the actual storage, distributed storage, which can, I mean, it can be abused for many things, let's say. We try to make it as flexible as possible. Unfortunately, block storage doesn't really fit in the picture, so I don't see it happening. We are more targeted for secondary storage. So we already have actually a use case with a company here in Germany who is using which is using SS cluster with our S3 interface, which is called Libres3, as a secondary storage for Citrix cloud platform. And we also have in the working SXFS, which is a file system. It's really promising. It's still beta, so don't use it in production. We started developing it in February, so it's only a couple of months of work. Obviously, SX cluster, as I said, has been in development for almost 3 years now, and we didn't get any bug reports since, even minor ones, since December last year, so it has reached a pretty mature state. SXFS instead has still a lot of work to do. It works really well as in read-only mode for now. It's incredibly fast because basically when you mount a file system, you are reading in parallel from all nodes and you can really see that you keep adding nodes to the cluster and the speed just keeps growing. In the end, you are always limited by the network, so as fast as your network can be. And we are still working on improving the writing performance, which is quite poor. We support, for now, only Linux, SXFS on Linux. We have plans to extend the support to Windows. So the idea that we had, actually, which you might like, is to integrate also SX drive with the SXFS. So it's what some people call the infinite drive. So the idea is that you get a cloud drive application that you can run on your desktop, for example, and for each volume, which you can think of as a directory after all, for each directory you can choose if you want to keep a directory, a copy of the directory local, so you want it to be available when you are offline, or if you want to just be able to access it when you are online. So the use case is typically people that store terabytes of pictures and movies, family movies, in their cloud drive, but they travel with a MacBook Air which has 256 gigabytes of SSD, and they simply cannot synchronize them, but they still want to have access to them while they are on the go. And currently this feature, as far as I know, is only supported by OneDrive in Windows 10 even, not in the other version, it was dropped because it caused some problems. And our idea is to implement this in SX Drive. So you will be able to choose which directory you want to synchronize locally and which one you want to access over the network. So yeah, anyway, sorry, I went a bit farther than the question was. But yeah, we have, talking about OpenStack, we are working on a Java library, Java client library, for our protocol, for the SX protocol. And we will be working also on a Python library. And when that is done, we plan to create a project on the, I forgot how it's called, the OpenStack development website, and register as an experimental project for OpenStack and integrate into it. But we will only target the secondary storage. Yeah?
My question is, do SX cluster going the same data on all nodes?
You can choose.
More space you have to focus based on all nodes, yeah?
So the question is, does a Scalable store all data on every node? Yeah. The same data on every node? No. The idea of consistent hashing is that the object is divided into many blocks, and then you basically create a map of these blocks which doesn't require an index. So the map is the result of a function. So you put the hash of the block into the function and you get the position of the block, okay? So this way you can have a file split across multiple nodes. Then you want a replica, so you take this map and you just shift it by some amount of positions. And this way, the block that in the first map was on node 1, with the shift will go on, for example, on node 3, right? And this is how you get the replica. So to simplify the answer, the idea is that if you have a replica 3 volume, and you, a 3-node cluster with a replica 2 volume, the data will be, one file will be, one copy of the file will be on the first 2 nodes, and another copy of the file will be on the second and third node, okay? Divide, exactly, yeah. Other questions? Yeah?
How are the clients connecting to the service? How do they find the data? If they connect to a specific node,
Mm-hmm.
data is on this node, will the nodes communicate and proxy request to the correct node?
Mm-hmm. Okay, so the question is, how do the clients find the data on the cluster? How do they find the location of the blocks? And how do they communicate with the target nodes? So the way our protocol works is this. We first, so we expect a DNS record with a round robin of all nodes. Don't be scared. The DNS record doesn't have to be updated continuously. So the client will detect automatically if one node of that DNS record is down, is dead, or has been kicked out of the cluster. So you don't have to continuously keep the DNS record updated, because otherwise you will have the problem again, the problem of HA, right? So the client queries the DNS record, gets a list of nodes. You don't have to provide all the nodes, just a few of them is enough to bootstrap the request, let's say. The client will connect to each node, to the first node in the list. It checks if it is a live node or not. Then it asks, where is the volume? So the volume that I'm trying to access, who has the metadata information for this volume, right? So the node, every node in the cluster knows which nodes hold the volume metadata. So they will they will get a list of, we call them volume nodes for that volume, and they will query directly those nodes. And when they query those nodes, they get a list of blocks, of the hashes of the blocks which make up the object. And once they have the hash, they can just put the hash through the consistent hashing function and get the whole map of the distribution of the file. So to give you the big picture, okay, of how it works. In the cluster, the files, the previous question was about how the files are distributed with replica, right? So all nodes contain a portion of the objects, right? But only a few nodes, so for replica 2 it will be 2 nodes, for replica 3 it will be 3 nodes, know the block list of an object. So if you choose a replica 2, there will be 2 nodes which know that object A has 5 blocks, and the hashes of the block are the D, A, D, B, F, blah, blah, blah. All the full hash, right? The SHA-1, we use the SHA-1. And once you have the hash of the blocks, you can just pass them to a function, and the function will give you the map, will tell you exactly on which nodes are the blocks.
Okay, then thank you very much.
All right, thank you.